The quick sections about continuities of one-sided limits, section 2.4. Now let's recall when we define the limits, we often means when x approaching a, limit of x equal L, it approach all sides from a. Now when we could define it as a left-handed or right-hand limit, where we use a minus to mean its approach a from the left, and the graph approach, whatever this value is L. Okay. Same thing, we could define the right-hand limits where x approach a from the right only. Okay, so that's a minus for left, the plus for right-hand limit. Okay, now essentially, here's a quick example why we need to do the left hand and right hand limits, because there are times that it only makes sense to approach the functions from one side. So here is a quick example. What's the coldest temperature that you can think of? That was the lowest temperature that we can have in the world. Okay. The answer is negative 273.15 degree Fahrenheit, or it's 0 degree in Kelvin scale, the so-called the absolute zero. That means there's nothing on Earth in this universe could have a temperature lower than this number. So the question is, how do we know? Right? So how do scientists determine that it cannot be colder than 0 Kelvin degree or negative 273.15 degrees Fahrenheit? Okay, so this is what we do. They do. They actually measure. In fact, actually, they do this with the gas. That means the air, not the liquid or solid. So let's say what they did is they measure the volumes of the hydrogen gas. Okay, and they compare, and then they measure the temperature. So if they take this air, right? So they measure the volume of the hydrogens, and let's say at 19.14, that is temperature is negative 40 degrees. At 20 liters, about 20.79 liters, the temperature is negative 20. 22.4, it's 0 degree, etc. So they were able to establish the functions of relation between the two, the temperatures and the volume of the hydrogen gas. Okay, then they can come up with the formula here. Basically, the volume could be calculated based on the temperature T. Or if you solve for T, it's the temperatures based on or depends on the volumes. Now the question is, as the volumes decrease, go from 29, 27, 25, 24, 22, you see that the volumes cannot be negative. So it can only be smaller, so from one side. So what happened if the volume getting smaller and smaller, from 29, now down to 19, how about 16, 12, 15, 11, etc. So as the volumes approach 0, what is the temperatures approaching? Okay, and so we were able to do that actually. So when V approaches 0, right? So from the right, and this time it can be from the right, because it's getting close and close from 0 on the right of 0, not the left. There's no negative numbers. So approach 0 from the right, when you plug in and do the math, it come out to be negative 273.15 degrees, right? You know, here's a quick fact, but it's not something. So actually, in 2003, the researchers produced a super cold gas that has the temperatures of about negative 273.149999999 1.55 degrees. So you can see that it's pretty close to this. And again, as the volume approaches 0, then we got the limit is this number. And this is the right-hand limit. Okay. Now, when we find the limits of, on one side, we basically use the same technique we learned finding two-side limits. So there's no difference. Okay, it's no difference. In fact, I think it's actually a bit easier. So look at this one, say how to find this limit of square root of x minus 2 of x squared minus 16, where x equals 4 from the right. So what we do again is when you have the radical, so it looks like we're going to rationalize the numerators, okay? But at the same time, we also might want to consider factoring the denominators. So one of the techniques is we either factor and cancel the common factors, or we rationalize the numerator denominator as the root. So in this case, if you look at the bottoms, it's a difference of squares, so it's factored x squared minus, x minus 4 times x plus 4, right? So the bottom here is x minus 4 and times x plus 4. And then the numerator is root x minus 2. So what I can do is I multiply, okay, to rational numerators, and multiply the top and bottom by the conjugate of this, which is root x plus 2. So you times root x plus 2. All right, so when we do that, you see we could actually not cancel, we multiply these out. Then we have what? A limit of, so that's a difference of squares, so we root x squared is x, and then minus 2 squared is 4. So you have x minus 4 in the numerator, and then we have x minus 4 times x plus 4 times root x plus 2 in the denominator. And so x approaches 4 from the right. Okay, so then we can cancel the common factor. Right, so when cancel common factor, so that's left with 1. And then you can do this direct substitutions here. Plug 4 in, so we have a 1 over 4 plus 4, then 8, and root 4 plus 2. So 2 plus 2 is 4, so I think we have 1 over 32. Right, that's the limit. Okay. Now, for the second problem, when we have the absolute values, then we have to rewrite this. Remember, the absolute values, there are two cases, right? So if you have absolute of x plus 1, this is equivalent to is x plus 1 if x plus 1 greater than or equal to 0, or equal to the opposite, x plus 1 if x plus 1 less than 0. Right, so there's a definition of absolute values, or in our case, if the numerator is split into these two, right, then this limits, or the function here, x plus 1 over plus 1, that would equal what? So if x plus 1 greater than or equal to 0, or if x greater than or equal to 0, the numerator becomes x plus 1. We have x plus 1 on the bottom, we cancel, so that becomes 1. If x is less than, sorry, this is not 0, it's a negative 1, right? So x greater than negative 1, and that's x less than negative 1. then the numerator will become negative x plus 1, cancel, we got negative 1. So essentially, these functions, if you grab the functions, that's what it looks like. Here's a negative 1. From negative 1 on, see this have carry a positive 1 value. So here's 1. Here's the line up to here, negative 1. And then if x less than negative 1, it has negative 1 values. And negative 1 values is down here. Right, so it's negative 1. So here, 1. And down here, it has negative 1. And since it's strictly less than negative 1, so it's an open circle there. Okay. So if you observe from the graph, you can see if x approaching negative 1 from the left, okay, where's the left? Here is negative 1, from the left is here. So getting closer and closer and closer to a negative 1. So the answer here is this limit equal negative 1 for the left hand limits. Right. Okay, next. Now we're going to define what we call a continuity. So what does it mean for a function to be continuous? You look at these two functions. They're not continuous at C. See here at C, there's a vertical asymptote. At C, well, there's a gap here. This is actually called jump discontinuity. This discontinuity at C, this discontinuity is at C as well, but it's different. This is the vertical asymptote. That one is a gap. Okay. In this case, you see that at C, the limit doesn't exist, right? It doesn't approach any values. And on the other side, here, the limit still doesn't exist. Why? Because it approach different values on both sides. You see that on the left, it's approaching these values. And on the right hand side of C, it's approaching different values. So the left and the right limit do not match, and therefore the limit doesn't exist. Okay, so this is called the infinite discontinuity. So we got to go to infinity. This is called the jump discontinuity. We think of that as a you can think of like how people walk on the curve, right? And here, it's this person to get to the other side must jump down here, right? There's a jump, so it's a gap there. So there's two types of discontinuity in this slide. Now, here's a third type of discontinuities. You see the graph still not continuous, so but in this case, it just has a hole. Then the dot is up here. So see that there's a gap here. So again, if you walk on the corner on the curve, you have to walk through. It's like the hole there. And so you have to skip that. Okay, so that's still discontinuity. Now in this case, notice that the limit exists because the limit from the left of C and the right of C, they approach the same place. It's closing this hole. However, the function values is different. The function values is up there. So that's why it makes the function discontinuous, because there's the hole there. However, this is an easy fix. If you want like the path to be continuous, all you do is you replace this dot, or technically you move this dot to put in here, you fill it in, then the graph becomes continuous. So this type of discontinuity is easy to remove. Basically shift the points down. It's called removable discontinuities. In this case, the function, the limit exists, but the function's values just not the same as the limits or x approach c. Okay. And again, you can see these are A, where function not continuous. There's a jump discontinuity at A, and there is a removable discontinuity at A. So here's a quick definitions. A function is continuous at a number A, if the limit of x approach A must equal f of A. Okay, so this means that you must show the limit from the left of the functions when x approaches A, and the limit from the right of A must equal f of A. Okay, so this implicitly requires that the limit must exist and f of A must be defined. Okay. So one way to determine whether the function not continuous is to look at f of A. If f of A is not defined, that means the graph is nothing there at that point, then the graph must be discontinuous. So that helps us quickly locate where the function is not continuous. For example, looking at this one here, look at the bottom x minus 2. I can easily see that when x equals 2, the function cannot divide by 0, and therefore the function is undefined at 2, when 2 minus 2 is 0. Okay, so if you ask me, okay, is f(x) continuous at 3? Then I would say yes, because by definition, all you need to do is you need to do two things. You need to figure out what's f of 3, and you need to figure out what's the limit of the function when x approaches 3. Notice that f of 3 means you plug 3 into the functions, and then you can do the math. 9 minus 4 is 5. I think the answer is 5. Then or n, on the other hand, you take finding the limit of x squared minus 4 over x minus 2 when x approach 3. Now I can still plug in by using direct substitution, so let's get to 3 as well. So that one means 3, no, it's 5, means 5. Okay, so f of 3 and the limit equals, so it's continuous, yes. Likewise, if you ask to determine whether the function is continuous at 2, in this case, let's say no. How do I know? Because the function is not even defined at 2. So that is what's f of 2. When you plug 2 in, you got 0 over 0. So that function is undefined. And because function not defined, so the graph is not continuous there. Okay. I think I'm gonna stop right here.